All right, good afternoon. So as you mentioned, my name is Josh Humphries. I am a software engineer at FullStory, and I work on our platform engineering team. And I thought I unlocked this beforehand. Okay. So I'm going to be talking about gRPcurl. This is a project that FullStory open sourced, and a lot of the content is actually about the topics that power gRPcurl, gRPC Reflection. The slides are kind of dense. I might talk kind of fast to fit all of it in 45 minutes. So if I skip past the slide and you were reading it while I was talking, everything will be available afterwards. There's a lot of links also and lots of other information, so slides are a good resource for digging into this stuff afterwards. So if you don't already know much about gRPC or protocol buffers, I'll go ahead and warn you, it might be tough to follow most of the presentation, but I will give an obligatory try at a 2-slide intro. So gRPC is a specification for RPCs, and what I mean by that is it's a protocol specification built on top of HTTP2. The specification describes how procedure calls map to the HTTP2 protocol. It also specifies language agnostic semantics around the life cycle of an RPC and cancellation and error handling, such as a canonical set of error codes for servers reporting failures to clients. Excuse me. It's also code generation tools. So there's a plugin or plugins for various languages. Obviously, we're interested in Go that generate Go code, server interfaces and client stubs from our protocol buffers. And there are runtime libraries. The gRPC runtime libraries for Go, they implement the client and server machinery, such as the persistent connections and the pluggable support for service discovery and load balancing for the client. And they also implement the transport protocol. So protocol buffers, we mentioned, what are those? First and foremost, it's an interface definition language. That means we can use it to declare the shape of data structures and server interfaces, but not express business logic. And chief among the tool set for protocol buffers is protoc. This is a compiler that takes your proto sources, and in our case, it's going to generate Go code. It generates code for multiple languages, and it's even extensible as a plugin protocol. And then it also includes runtime libraries. And we're going to look at some of those because they're pretty key to reflection. And they provide support for the serialization format. Protocols, buffers have a well-known or well-described efficient binary format, as well as a text format for human consumption and a mechanism for mapping them to JSON. Okay, if you want to know more, feel free to visit the main website. There's tutorials and other stuff. You can also check out, there's an online book called Practical gRPC, and full disclosure, I'm one of the authors, along with 4 other knowledgeable gRPC community folk. Okay, so now we're going to talk about all the interesting stuff. Excuse me. So originally at FullStory, we had an App Engine app. It's fairly simple. The task queues and Cloud Data Store, those are services provided by App Engine. And we quickly outgrew this architecture, right? The task queues were for background processing, Cloud Data Store for persistence, the App Engine services themselves are HTTP 1.1 services. Before long, we added search capability. So we had a Go search backend. It would translate search criteria that the user provided, turn that into Lucene queries, dispatch it to Solar Cloud. And that all used URL fetch, which is also another one of these services provided by App Engine that allows App Engine services to talk to other things via HTTP 1.1. So at FullStory, we wanted to use RPC because several FullStorians are aware of its benefits and have even built RPC libraries in the past. So it's easier to use programming model. To initiate a call to a server, it's just a method call. You don't make developers worry about things like building URL strings or query string parameters or even encoding post-body payloads and decoding responses. You just invoke a method and all that's abstracted away. And we can also leverage code generation. The value there is we just describe our server interface and we can then generate the server bindings. So that's all the code that will accept our HTTP request and marshal it into the parameters that were in the server interface, and invoke the method. And similar, we can generate the entire client side. Client stubs that do the same thing, where a client invokes a method, and the generated code handles taking those parameters and building an HTTP request out of them. So, a couple years ago, January 2015, we built a bespoke RPC system to connect all of our services, App Engine to backends, etc. It used HTTP 1.1. As I mentioned, we were using App Engine, so some of the clients were App Engine, and their only mechanism for talking out was via the URL fetch service. This predated gRPC, but only by a few months. And then another year later, gRPC 1.0 would be released. So if we fast forward to a couple years, we've actually adopted gRPC in a lot of places. We've moved a lot of functionality off of App Engine into Kubernetes. New stuff we build, we use Kubernetes services, and we use gRPC to connect all of our microservices running in Kubernetes. We do still have some code using that bespoke RPC system I described, but we're in the process of moving all those to gRPC as well. There's a link to a gRPChan project. We use this not only for App Engine services to consume gRPC protocols, but this open source library also allows App Engine to expose gRPC services over HTTP 1.1. And if you're curious why anyone would want to do that, let's just say we're migrating stuff into Kubernetes from App Engine, and that's just step one for changing the tires while the car is still moving. So pretty quickly, we have an internal project called Commander that grew to be a very large gRPC server, mostly in terms of methods. Like the proto interface for it was very large. It's an internal command line tool. We use it to administer the FullStory app. And what it does is it's a lot like if you've ever used Google Cloud Platform. There's a gCloud tool. It's similar to that. It's like an Uber command line tool that lets FullStorians do what they need to do admin actions, do change configuration, etc. inside of our app. The architecture of this tool is pretty simple. It's a thin client command line tool. What it does is just packages up the command line into an RPC request, and it sends it to the server. Commandant, that server counterpart, that's what does all the logic. It's the wide gRPC service interface is implemented by it. And it will, in the process of satisfying a request, talk to FullStory backends or Google Cloud services. So here we can see just a real simple example of what that looks like. So the Commander client, very simple. We give it an action. I want to list some people. I might give it an email domain. And this maps in pretty mechanically to a gRPC request. So someone invokes that command line tool, and it's going to result in this RPC request. There's an endpoint in Commandant for this people action, and we can see that the requests parameters are mapped pretty directly from the command line flags. So it's mostly boilerplate, the command line tool. Every time you add any sort of new admin function in Commandant, it's a bit of a chore to go and also do this rote process of mirroring the request proto with command line flags and writing the code to package up those flags into a request proto and invoke the corresponding method. This kind of rote boilerplate just adds friction if we want to add new capabilities. So in the ideal world, that Commander would be completely dynamic. So the Commander client could just ask Commandant, what are all your RPC actions that I might care about? And it would use that metadata, including full RPC schemas, request and response types, to define its set of supported command line actions and command line flags. Then it could parse the flags. And then finally, the action, instead of it being all boilerplate, it would actually be just a single generic handler that knows how to package up those parameters. It reflectively creates the request and dynamically invokes the RPC method. So the ideal test here is that we don't want to have to update or deploy the command line client just because we add functionality to our Commandant service. So anyone who's used gRPC and protobufs knows that what I just described is not very straightforward. Usually you would use protoc. It processes your proto files, and you generate a Go interface for RPC, Go structs for all the requests and responses. But here we're going to need to be able to invoke RPCs in a case where we don't even know, we have no Go interface, we have no Go structs defined. So in this process, there's no obviously usable RPC metadata. There's no obvious ability of how we would reflectively create a request or invoke the RPC. So obviously, protoc is not a good fit, so we need to do something different. So the answer lies in protocol buffer and gRPC reflection. The next two sections are going to be the meat as far as dense technical information. So what's protobuf reflection? Protobuf reflection is composed of these two topics, descriptors and dynamic messages. So a descriptor, you can think of these as like nodes in an abstract syntax tree for the proto language. They're the language model for protocol buffers. There's one for each kind of source element, meaning messages, enums, services that you'd see in proto source. There's a message descriptor, enum descriptor, etc. We can kind of take a look. This is the definition in the protobuf repo for all the descriptors. And just as a quick example, this is the definition for the file descriptor proto. And we see all the things we'd expect, right? So a file descriptor proto that corresponds to our source code, we'd see our import statements. We have these dependency fields. If we declared a package, there's a package field. All of the messages, enums, etc. we define are modeled with their own descriptors inside this. And in addition, so they're protos themselves, which is kind of neat. And that's also how you write protoc plugins. So just a little bit of a trivia. Protoc will parse all of your proto source files, create descriptors, and then just hand those off to a plugin. And then it's up to the plugin to examine those descriptors and figure out what code to generate. So a dynamic message. So we know a regular message, it's something that protoc generates. It's a Go struct. A dynamic message, what we need here is a data structure that can represent any kind of protocol buffer message. We will use a message descriptor. That's how the dynamic message knows the type it represents, what its fields are and their fields types. And the data can essentially be represented by a map. Every field in a protocol buffer message has a unique tag. So we see the keys are int32s. And then we could just store empty interface because the values might be ints or bools or strings or even nested messages. So with something like this, application code can basically represent any kind of message, even one that, there's no Go struct generated for it. So the Java and C++ runtime libraries for protobuf actually have pretty good support for protobuf descriptors and dynamic messages. You can do interesting reflective stuff. But we kind of ran into a problem. We can't build our commander client in Go, which is what we use at FullStory, because there's not really much support in Go. So we do have limited support for descriptors, but there's no support at all for dynamic messages. Just to kind of dig in a little bit, this is a file produced by protoc for Go. This is the support for descriptors. For every message type in your protocol buffer file, it'll create a message like a struct, and it'll give it a method called descriptor. And we can see from this, bag of bytes, slice events, it's not very obvious how we'd use this. It's not meant to be directly used. It's actually meant to be, you're intended to use this separate package. The protobuf runtime includes this descriptor package, and it has a single exported method. You can tell it, I want the descriptor, you give it a message instance, and it does the job of taking that byte slice, decoding it into a file descriptor proto. That slice of ints that was returned is actually a path. That's how it can navigate the file descriptor proto and find exactly which message descriptor we care about. So this is the support for descriptors in the core runtime. Oh, sorry, I wanted to show a little bit more in that generated file. So some other things that are interesting to observe in what protoc generates is that at the end of every file generated by protoc, this is the bag of bytes that represents a file descriptor. And we see that these global registries. So this is the proto package as part of the protobuf runtime. It registers files by names. So this is another aspect of how descriptors are supported in the core language, the core library. So you can ask by name for file descriptor, and you'll get back the encoded form. And there's also global registries for things like all the extensions you define, as well as all the enums and types, message types These are all, as we can see, in an init function. So whenever you generate code with protoc, you link it into your program, and then suddenly your program has access through this global registry to access information about all these types. Okay. So I said it doesn't have the support for dynamic messages and limited support, and caveat that there is a version 2 of the Protobuf runtime API coming. I think work began this month, but anyways, we had this issue. We were trying to build a dynamic client for Commander about 18 months ago. So we had to do something different. So it was February 2017. I had all this on my mind, and I ended up going to vacation, actually. I took a vacation to Mexico. And despite the fact I was in a beautiful place and went to the beach and all that, whenever it would rain or early in the morning, I actually would just break out my laptop and kind of hack in a personal GitHub project called Protoreflect on making this stuff work. And so I'm going to talk a little bit about what that repo has. It's a few packages, and those are going to be key to how we do Protobuf and gRPC reflection. So there's a package for each of the topics we just mentioned. There's the descriptor package. We already saw that there's descriptor protos for everything. This package provides rich descriptors. So if you have a file descriptor proto, or more specifically, let's say you have a method descriptor proto, and you ask, what is your request type? All it has is a string. It's a fully qualified name for the message. If you then want to introspect and say, well, what are the fields of this message and what are their types, you have to go search through a file descriptor for that message. It might not even be the same file descriptor. It could be that the method's request type was actually defined in some other file that it imported. So these rich descriptors are fully linked. Right? We can take those descriptor protos and wrap them in rich descriptors, and the idea here is that if I get a method descriptor instance and I ask it for its request or response type, I get back a message descriptor, and I can then immediately and easily look at all the metadata in that descriptor. So there's also numerous accessor functions that we can get at all those global registries. So I showed before that protoc generated code gets registered in global registries that you can access through the proto package. And this package allows us access to that. So we can load a file descriptor by name, and instead of getting back a proto, we get one of these rich, fully linked, and useful descriptors. And same for those global registries of message types and enums and extensions. And then we can also, for more advanced usage, just take a raw proto. There's APIs for kind of upgrading it. You have to give it a proto, and then you have to have already upgraded all of its dependencies. And protoc can also produce what's called a file descriptor set. And so it's also possible to create a file descriptor, a rich descriptor, from a file descriptor set. We read the file's bytes, unmarshal them into this file descriptor set proto, and then we have API to turn that into a rich descriptor. So there are a couple other ways we could create descriptors. One of the more interesting ones is a protoparse package that we could use, and it actually allows you to parse proto source code. The output is a set of rich file descriptors. And then for more advanced usage, if you're programmatically constructing proto descriptors, you can do that with just protos and build full file descriptor protos. But there's a builder package that makes that a lot easier. So that's descriptors. Dynamic messages. There's a dynamic package in the Protoreflect repo, and its main type is this dynamic message. Now this type has a pretty wide API for setting and querying field values. You can ask for or set fields by name or by that int32 tag or even with a field descriptor. And it also provides methods for the serialization formats like the well-defined Protobuf binary format, text format, JSON, etc. Excuse me. Now this dynamic message, it implements the proto message. This is an interface defined in the core Protobuf runtime. Every message, every struct generated by protoc implements the same interface. And the dynamic message implements the same interface. So in a lot of places, APIs that accept a proto message, we can instead provide a dynamic message, and it mostly works. There are some APIs that really expect a proto message to be a generated struct, and they want to reflect over struct tags. But in many places, you can substitute a dynamic message and things work. The way you create a dynamic message, As we mentioned, like you need a message descriptor. The dynamic message has to know information about its fields and what type it represents. And then there's also a way to create one with an extension registry. So the extension registry is just so that we can parse extension fields in a serialized message. The way the Protobuf runtime normally works, we saw earlier that there's a global registry of extensions that all the protoc generated extensions get registered into. So normally when you have a generated struct and you're unmarshalling that from bytes, the Protobuf runtime will consult that global registry. That obviously doesn't work for dynamic message. So we can use an extension registry, which is basically a database of extension field descriptors. So the next topic we're going to talk about is gRPC reflection. This is an extension. Like we're going to move, building on Protobuf on descriptors and dynamic messages, how do we do dynamic gRPC? So first of all, there's two more concepts we're going to talk about. So service reflection it's an interesting concept. So it's actually a gRPC service. I'm just going to go ahead and show. So it's in the gRPC Go repo, so it's pretty easy to import into your Go code. And it's just it's a gRPC service defined in Protobuf. It's a streaming call, so the protocol's a little weird. It's meant to be chatty, so you have a persistent stream where you're asking the server for what services do you expose, or what kind of, given this file, can you give me back the descriptor? So luckily, if you want your server to support this, or the whole purpose, sorry, I should have said this first, is that we want our clients to be able to dial the server and say, give me your RPC schema so that I can then dynamically invoke RPC methods. And luckily, we don't have to build our own. If we have a Go RPC service, this reflection package, you import it, and you got one line, and this adds support to your server for reflection. This allows any dynamic client to work with it. Okay, so service reflection is optional. The reason it's optional is because all we really need for dynamic gRPC is we need service descriptors. Fundamentally, we're looking for what are all the methods the service has, what are its request and response types. So there are other sources for service descriptors, but service reflection is a very convenient one. We can just have the client ask the server, give me your descriptors so I can understand your RPC schema. But if a server does not support our service reflection, we already talked about other ways to get descriptors. We can parse proto source files from them. We can load file descriptor sets produced by protoc, create them programmatically. So in addition to service reflection, the other component here is a dynamic stub. So the protoc will generate a stub for every service, and it has therein a method for each RPC method. So you use a particular interface to invoke a particular method. The dynamic stub will work differently, right? We need something that we can invoke any kind of RPC method across any kind of service. And ideally, it would provide the same semantics and API as those interfaces generated by protoc. Now, in order to tell it which method to invoke, we're also going to need to tell it at each invocation, we give it a method descriptor. And that's how it knows what it's doing. And again, we don't know the RPC schema ahead of time, so we're going to be using dynamic messages, which we talked about earlier, as a way to actually represent request and response data. So we have, similar to what we talked about before, there's two packages in the ProtoReflect repo that kind of implement what we just talked about. So the gRPC reflect package, it primarily provides a client. Now this thing isn't strictly necessary. The server reflection is just a gRPC interface. And so we could use this thing. This is what protoc produces. This is the gRPC client stub. But it's a little bit awkward to use the way the streaming interface works. So we can wrap it in a gRPC reflect client, and that provides a much simpler API, much easier to use. This has got some other features, such as everything it returns is a rich descriptor, not just a raw proto. Again, that's going to make it much easier to use and navigate the RPC schema. And it'll even auto retry. So if you ask the server for a descriptor and the stream is for some reason broken, it will auto recreate a new RPC stream and ask again. This is just a sample code. showing how it's used. This function is going to take a server address, and it's going to return a descriptor for all the services that it exposes. Here we see we're dialing the server using the standard gRPC package. We take that client connection and use it to build a stub, and then that's what we're wrapping with our gRPC reflect client. And its methods are very similar. So instead of having to send messages on the stream, which is what we'd have to do if we were using the stub, to say, I want a list of services, and now I want a descriptor for this element, we just invoke a list services method and get back all the names as a slice of strings. There's also several resolve methods where we can give it a fully qualified element name and get back a rich descriptor. There's also a package for implementing the dynamic stubs. It's called gRPC dynamic. It's probably not very surprising that the type is called stub, and it has a factory function. We give it really a gRPC client connection. We're going to dial a server, and then we're going to tell the stub use that connection. The actual signature is this channel interface. That's just for flexibility. That interface is defined with just the two key methods that the client con provides that we need to do to invoke an RPC method. So the stub has 4 other methods, just one for each kind of RPC. It has a simple one for unary RPCs, and by that I mean a typical RPC is one request, one response. But then when gRPC supports streaming, so there's also, we can have RPCs where the client can upload any number of messages as a stream, or vice versa, where it's the server that can reply with any number of messages as a stream. And then gRPC also supports bidirectional streams. And that's not just streaming upload, streaming download. It's also fully duplex, so you can arbitrarily send messages back and forth, one of the cooler features of gRPC. The method signatures here resemble the method signatures of generated stubs. We'll see a key difference is that they all take a method descriptor. That's how it knows which RPC method we're actually invoking. So we see here signatures for unary and client stream. We have the same thing for server and bidirectional streams. Okay, so now that we've gotten a foundation with protocol buffer reflection and gRPC reflection, we can kind of see how it comes together. So we started our exploration of dynamic gRPC, wanting to build a client for FullStory's commander admin tool. But it turns out all those things we just looked at for how we build a dynamic client can also be used to dynamically talk to any gRPC server. So that's actually ultimately the tool we built. It was more generic than just a commander client, and we open sourced it. It's called grpcurl. It's 2 things. So first of all, it's a command line tool, grpcurl, meant to be like curl, but using curl with gRPC is pretty hard because of the format is generally a binary protobuf format. gRPcurl allows you to send requests and responses, or it presents them to the user as just JSON, which is easier for both humans and scripts to produce. Dynamic command line tool. There is in the gRPC repo a similar tool called gRPC CLI. It doesn't support streaming, but it does support other functions that gRPcurl supports. But another advantage of gRPcurl is it's not just a command line program. That's probably what it gets used by far the most for. But it's also a package to simplify construction of other dynamic clients. So we're going to talk just a couple minutes about this gRPC curl package, gRPcurl. So in that FullStory dev gRPcurl package, the key concept is a descriptor source, or that's one of the key abstractions. We can see here its interface intentionally resembles that gRPC reflect client that we looked at before. So we can ask the server for a list of its services, and we can resolve symbols such as service names into a fully qualified descriptor. The package has 3 ways of creating a descriptor source, and the first one is the simplest. So if your server supports server reflection, then you give it a gRPC reflect client, and the descriptor source essentially just delegates all those calls to the gRPC reflect client. But if the server does not support server reflection, we can still, like we talked about before, we can build descriptors from protosets and parsing source code. So we have factory methods here to create a descriptor source from compiled descriptor files or file descriptor sets, or even from proto source files. We can parse and compile those into descriptors. And then the meat of this package is a singular function for invoking any kind of RPC method dynamically. So unlike our gRPC dynamic stub, which had a different signature for each kind of RPC, this has a much more complicated interface, or signature rather, but it allows us to invoke any kind of RPC. So kind of the expected things, we give it a client connection. That's what it's actually going to, the connection it uses to dispatch the RPC. We're telling it which method to invoke, and it uses the descriptor source to actually, query for and understand all of the request and response schemas, or the request response type for that method. And the other key piece here is this request data. This is actually a factory function. So we call invoke RPC, and it's going to in turn invoke this request message supplier function to get a piece of request data. The format of that is actually JSON, and it will handle using a dynamic message to turn that JSON, parse it into the dynamic message, and then marshal it back into the binary format, which is what the gRPC server is expecting. And for a normal RPC, it'll just call that function once, get the single request, excuse me. But for a streaming call or a client streaming call, it will actually just call that function repeatedly until it returns the EOF. So that's the package, and then it's wrapped by this CLI we talked about. It's obviously just a normal Go program. Use go get or go install to build it and install it. The only kind of caveats to keep in mind is that all the command line flags have to be specified on the command line first. It's just using the normal Go flags package, which requires that. After your command line options, the arguments it accepts are the address, the host and port of the server you're trying to talk to, and then whatever it is you want to do. So in addition to invoking an RPC, we can also use grpcurl as a command line tool to explore the RPC schema. So I'm going to show that. Okay, so I have this very simple demo server. I've already built grpcurl on this machine. So the first thing I'm going to do is I'm going to use that list action. So what it's going to come back with is all of the gRPC service interfaces supported by this server. Now notice this server supports reflection, and that's actually how we got this list. Basically, grpcurl asked the server, using that interface, what services do you expose? Now, if the server did not expose that interface, grpcurl would give us an error saying it doesn't work. And then you can supply to grpcurl proto source files, for example. Sorry. All right, so we can see the list of services. What else can we do with grpcurl? If we do list and we give it the name of a service, it will give back all of the methods in that service. So this, looks like pretty typical for a bank service. Let's try to invoke one of the methods. I'm going to try and get a list of accounts. All right, this is what an error looks like. So if a gRPC server sends back an error code, grpcurl will first show the string, like the textual version of that error code, and then any custom message that the server has included, which in this case is nothing useful. So that's what happens on an error, and it also exits with a non-zero exit code. So now I'm going to try again, and this time, kind of like curl, I can give it a -h argument, and this will end up sending request metadata. So I'm giving it my super secret authorization code, and I get back nothing. So I have no accounts with this bank. So let's remedy that. So I see up here in this list of methods, there's one called open account. So I can use this describe verb with grpcurl, and I give it any symbol name, and in this case, it's fully qualified. That's why it has the service name dot method name, similar as when we invoke the method there. And this comes back with, tells me details about them. Right? It's a method, we knew that, and it tells us information about the request and response type. All right, so I actually want to send a request, so I'm actually going to look at this guy. We want to actually say, what does that request message look like? So that spit out a lot of stuff. If we look at this, it's telling us it's a message. What this is actually a descriptor proto, but in JSON format. So it has asked for the descriptor for the open account request message, and it's simply printed out in JSON format. So It's maybe a little bit hard to glean, but we can see it's got the message name, but more importantly, it's got two fields, right? Initial deposit and since is an N32, and the type, which is this enum account.type. Now, that's useful, but it's still kind of clunky. I now want to create a JSON payload, because that's how we pass data with gRPcurl. We can just give it a JSON document. So what we can actually do to make that easier, make our lives easier, I'm going to repeat that same command, but this time I've added this message template argument. So this is obviously not as useful for scripts, but it's useful for humans if you're kind of doing exploration on an RPC API. If you use that, then after it dumps that message descriptor, it also provides us a JSON template. So this is basically the structure of the message in JSON format with just default or 0 values for the fields. So we can actually then use that as the basis for then constructing a valid request that we want to send to this service. So now that we know that, we're actually going to invoke the RPC. So when I did get accounts above, you'll notice I didn't send any data. Like curl, you can pass a -d argument, and it has the contents of the request in JSON format that you want to send. But if you don't specify it, it'll just send a single empty request message to the service. In this case, I want to send the request message. I could just do -d and put in a string that is the JSON request. But if I do an @, that tells gRPcurl to read the request data from standard input. So, excuse me, I'm going to run that. It's now waiting on me to provide request data in standard input. So I'm going to open up an account, a checking account with $100 in it. And it echoed back. So the server gave back a response that tells us the account number is account number 1. It's got the balance we expect. So that makes sense. Let's be responsible and maybe open up a savings account too. And that gave us account number 2. So not very secure, very guessable account numbers. But now we've got 2 accounts. So let's go back and do that initial get accounts. Oops, sorry. So yeah. So I reran that same bank.getAccounts RPC, but this time instead of an empty JSON object, I actually see my account numbers 1 and 2. So now presumably I could use gRPcurl, or I wouldn't use this really, but if I had a script that needed to do something with this service, I can poke around at the bank. So I mentioned that gRPcurl supports streaming. Sorry. So let's take a look at that, at streaming. Way back here at the top, when we listed the services, one of them was this support service. So if we take a look at that, sorry. Okay, so we did list support. If you recall, we give it a name of a service, and it's just going to list all of its methods. This, in case it has a method for, looks like maybe an interactive chat with one method used for support agents and another method used for customers. So if we actually take a look at this, we're going to describe the support.chat customer. And so yeah, as we can see, it's a method like we saw before, but this time we see that it's both client streaming and server streaming. So it's actually fully duplex bidirectional streaming RPC. So let's kind of play with that. I'm going to actually invoke chat customer. We're going to pretend I'm a customer with the bank and I can't use their website. I have a problem. So I'm using this -d with an @ again. Again, that tells gRPcurl to read the request from standard in. So now I can initialize a chat session. And so as you hit enter, interactively anyways, because it's reading new line delimited JSON documents for a stream, reads the first one, send it to the server, and I immediately get back, we've created a chat session. All right, so now as a customer, I can cry for help. So this time, I didn't get anything back. Is anyone there? So it turns out it really helps if I want to get a response for there to be a support agent on the other side. So I'm just going to, this time I'm invoking that chat agent method, and this time I've got a different authorization token. At this time, this is my super secret token to log in as a support agent. And the support agent's interface, it can accept, what is the oldest customer that's been waiting on a support agent, and I get a session. I can see that the customer is crying out for help. So let's send this person some salutations so they know that there's someone out here. And at this point, we have two bidirectional streams to our server that gRPCurl has open. And basically, the way the server works is as we send it requests, it just pipes it via channel. It's a Go server to distribute the messages. So as a support agent, type a message, I can immediately see it for the customer. I'm going to go ahead and just finish up our mock conversation here because I can't figure out how to use a website. And the chat agent, he happens to know all about foo on the website and knows the magic incantation. And then we're just going to pretend that the customer understood that. So this last message we sent it basically ended the session, and we can even see that the agent has been notified. So the server sent it a response with that final message, and then session ended. So anyways, that kind of shows off the features of gRPCurl. Obviously, it's pretty clunky to do as a human for actually doing bidirectional streaming. But the real issue is, or the cool thing is that you can put it in a shell script. You can have a pipeline that uses JQ to emit a stream of JSON, and then pipe that into gRPCurl. So it basically makes gRPC for scripting purposes a little more accessible. Okay, so that was gRPCurl and gRPC Reflection. There's a lot of information in the Go docs for those packages I described. And if you have any questions, I'll be around if you can find me, but if you can also file issues on our GitHub projects with both FullStory Dev and this ProtoReflect project under my personal account. And I mentioned earlier that there's actually a version 2 of the Protobuf API. So if you want to follow along and see what this will look like in the official library soon, which will vary a little bit from how what I described, there's links in the slideshow for how to do that. And like I said, the slides will be available along with all the slides from GopherCon afterwards. So thank you very much.